Well, hello and welcome YouTube to Mr. Robinson's Q&A Power Hour. This is for Integrated Math 1, and their material has been focusing on geometric sequences, and we're now going into graphing exponential functions and doing things like that. I don't know if they would have asked any questions based on exponential functions because it just happened over the course of the last 2 days, but we've been really dealing with fractions and exponential properties on top of it, trying to go without a calculator as often as possible. So we'll see what kinds of questions they threw into here. I saw there were 21 questions total, haven't read them yet, so I'm going to explore them with you. I want to try and go as fast as possible, as I always do, but as I have not seen the questions, I don't know what kinds of answers they're going to need based on the questions that are asked. If you don't know what the Q&A Power Hour is, basically every 2 weeks my students submit me questions and I answer them for them. Our last video was actually a month ago, 4 weeks ago, because we did have a week off and we had a week of testing where we did group tests and individual tests. So I didn't count those plus the week off. So the other 2 weeks outside of it did count in. So here are the next 2 weeks. And then I'll be recording another one 2 Fridays from now. At least I assume so. Okay, so let's see what they have here. We are going to start with, let's see. First question asks, what does n minus 1 represent and do you need to add it? Do you need to actually use it and implement it? So for those who don't know what n minus 1 represents here, I'm sure that the student is asking about the explicit rule for, specifically, we've been talking about a geometric sequence, such as f of n equals f of 1 times r to the n minus 1 power. This also applied for arithmetic sequences at the time where there was a common difference instead of a common ratio that looked like this. Now the question is, and there are two questions. What is n minus 1 and do you need to add it? And I'm assuming you mean, does it need to be, I might have to sneeze, does it need to be inserted in the equation itself? Well, the answer is yes, and no to that last part. Does it need to be inserted? It does, as long as you are referring to the first term here, and it was agreed upon by our math department that we would refer to the first term and not what is called the 0th term. There is an alternative to this one when you can use what's called the 0th term. It's a theoretical term because our list starts from the first term, but if we start from the term that would have occurred before, then you can just raise it to the n power, which is actually going to mimic a lot more your y equals a times b to the x power here. You could also do the same thing here, and if you use f of 0, it actually mimics that more of y equals mx plus b. So you might be asking why we don't use that. Well, we want to start just talking about that first term in the list and really use that as the sequence. And in geometric sequences, the 0th term tends to be a fraction quite a bit because the sequence can't attend for, when you're doubling numbers, maybe that number before was odd. The first number was odd, and then after that, it's all fractions. So they generally don't do this here. So you have to use n minus 1 if you use the first term, which we've been using, we've clung onto, the book clings onto as well. I've taught both before, but let's just use this one. Now, what does it represent? Well, n, hold on a second. I have a student that I tutor who's actually messaging me right now. I'm going to leave them off to the side. What does it represent? So remember that n represents your term position. So if n is 1, we're trying to look at the first term. And f of n, by the way, is the value of the nth term, whichever term you're looking at. So if I said f of 1, for example, when n is 1, that means the value of the first term is, and then let's say it's 5. And then the value of the second term is 10. And the value of the third term is 20. The 1, 2, and 3, those are the n's. Those are the n's. The f of 1, f of 2, f of 3, 5, 10, and 20, those are the value, those values, 5, 10, and 20 are the f of n's. F of 1, f of 2, f of 3. So anyway, n represents the term position. Why do we use n minus 1? I don't know if you asked that. Oh, what does it represent? So n minus 1 represents kind of using, not referring to the term before, but because n is the term position, when we try and find something like f of 5, we're trying to find the value of the fifth term. The exponent represents how many times we're going to multiply by our common ratio. If I want to find the fifth term, I'm going to multiply by the common ratio 5 minus 1 times. That's 4 times. I'm going to multiply 4 times because I begin on the first term. If my first term is 5 and I double each time, how many times will I multiply by 2 to get to the fifth term? I'm going to multiply just 4 times to get to the fifth term. I'm going to multiply by 2 4 times because I start on the first term. The distance between 5 and 1 is 4. And that's what the explicit rule says. It says start from the first term and multiply by your common ratio a certain number of times. That's why we use it. And that's why the 0th term, if we had f of 0, that's why we would multiply to the nth power, because to find the 5th term, I'm going to multiply by my common ratio 5 times. If I had a 0th term right here, it would, I guess, be 2.5. I'm just going to write it as 2.5. I'd have to multiply by 2 5 times now. 1, 2, 3, 4, 5 to get to the 5th term because I started on the 0th term. So that's the whole goal there, guys. I'm not going to get too deep into it outside of that. That was deep enough, I think, as is. But n represents the term thing. So n minus 1. In some cases, it could represent the term before it. But the way that we're using it in an exponent, it's more so representing the number of times we're multiplying by our common ratio. And that explicit rule is just describing it in that way. I hope I answered your question there. Okay. Next question is, when you write the explicit formula as a of n, I think we say a sub n, but you couldn't write that, I understand. A sub n equals a sub 1 times r to the n minus 1 power, and you replace the a's with f's, does it mean the same thing? Shoot, I shouldn't have undid that last thing. Yeah, they mean the same thing. So I just wrote before, this was f of n equals f of 1 times r to the n minus 1 power. This is called function notation. F of n with the parentheses. It's not multiplication. It's just notation means the way something's written. This is called function notation. They have another one called subscript notation that says a sub n equals a sub 1 times r to the n minus 1 power. Do they mean the same thing? Yeah. It's just a different notation. It's a way that something looks different. You know, just like how when we do divided by, sometimes we use a symbol like this, sometimes we use a symbol like that. When we use multiply, sometimes we use this, sometimes we use that, sometimes we use that. Just different notation. It's just a different way something's written. And you don't have to use A. You can use any letter you wanted. I can use F here if I wanted to. I know some books might use the letter T. T for the terms or something. T of n, or T sub n and T sub 1. It doesn't matter as long as it's a consistent thing and you stick with the notation as long as you started with it. Yeah, these are equivalent. One versus the other. You see a lot of subscript notation appear in theorems. You see it appear a lot in physics. Function notation is used more in math when it comes to, I don't know, it's used a lot more in math than other things I can say. Yeah, why are there two notations? I don't know. Someone thought of something, someone else thought of something else, and that was it. That's all she wrote. Yeah, they mean the same thing. Okay, what's the difference between arithmetic and geometric? Now, as far as the sequence goes, an arithmetic sequence is a sequence with a common ratio. A common ratio. That means, or excuse me, a common difference. Excuse me. An arithmetic sequence has a common difference. That means you're adding the same number over and over to get from one term to the next. You could be adding a positive number or adding a negative number, which appears as subtraction to us, but you're adding the same number over and over. A geometric sequence has a common ratio, which means we're multiplying by the same number over and over. It might appear like sometimes we're dividing, like if I'm dividing by 2, but that's the same thing as multiplying by 1/2 as well. Geometric sequences have that exponential behavior to them, whereas arithmetic sequences have that linear behavior to them, because that common difference means it's just a rise and run, or a fall and a run. And that's the difference between the two. Okay, next question. Can you explain the difference between geometric sequence? Well, I just did. Between geometric sequence and arithmetic sequence. Go ahead and look at the timestamp where I answer it right up here. It's the same thing. You guys should, and I'm not saying this Q&A isn't meant for you guys to learn things. I really hope you're learning this, and I hope you're not asking a question you already know the answer to, because you should know those ones. If you don't, I hope you learned it. All right, can you show how to do the r equals blank? Oh, r equals blank equals blank. Yeah, what I'm trying to do, so listen up for those who are not in my classes here. So let's say I gave you a sequence. I'll give you that 5, 10, 20, 40, etc. And I say find the common ratio, r. Now, hang on. Give me 1 second here. I want to sniffle a little. Okay. Okay. Now, r, a common ratio, represents what we're multiplying by from one term to the next. I am fully understanding that students know what we're multiplying from one value to the next. I get it. I know that you do. Because it's 2. But there will be times when you don't know what it is. And I want you to have a way of knowing what it is in every condition and scenario. So show me that you know how to do it. Show me that you have a way of finding it even if you don't know. And here's the thing. So they say that the common ratio is 2. And I say, how do you know? Here's what a lot of people will say. They'll say because 5 times 2 is 10. And whatever, 10 times 2 is 20. But here's the problem. you can't tell me how you found out it was 2 by using 2 in your explanation. It's like defining a word, having the term that you're defining in its definition. Like if I described you to tell me what something, what salt tastes like, and listen, I don't have a good answer for you either, outside of saying it tastes like something salty, right? You have to come up with something else that doesn't use the word, because that's not describing anything new for someone. It doesn't show me how you got the number, not how you knew what the number was, but how you got the number. I don't know how you got this number. So what I've been trying to have them do, guys, based on the question, is like when I test them, I'm using a system called EdgeElastic. And on EdgeElastic, I'm giving them blanks to fill in. I want them to fill in a blank here to show me the division of 2 numbers to get their common ratio. If they know the number's 2, that's great. How can you get 2? Well, 5 times some unknown number is 10. 5 times some unknown number is 10. What is that number? This is an algebra equation now. You can divide both sides by 5 to figure it out. You don't have to set it up like an algebra equation, but that might help you solve it. So what are those 2 blanks? One of them is 10/5, one of them is 2. So what I'm asking you to do is show me the division to get from one value to the next. You can write 10/5, you can write 20/10, you can write 40/20. To find out how to multiply from one number to the next, you divide one number by the one before it to figure it out. All of these will equal 2. You only write one of them, but that's the point. Why do we have to do that? Because there are some other numbers that are going to be a lot harder to figure out common ratio wise. If I give you another sequence right here, it goes from 5,000 to, and unfortunately I don't know what all these numbers are going to be here. I should have done this. To, well, I'll do one that I kind of know. To 4,000 to 3,200. Honestly, I wouldn't know what comes after this myself. Oh, wait a second. To 2,560. I don't know if that's right. I'm going to check on that one. That actually might be right. So all these numbers here, and ask what you're multiplying by, right? Still, what are you multiplying by? What's the common ratio? It's not obvious anymore, right? So times R times R. So set it up like an algebraic equation. What I generally recommend for my students, because I ask them to write it as a fraction, is to choose the 2 smallest integers possible, because generally it's easier to reduce smaller fractions than larger ones. But these 2 numbers are so perfect as far as they're just zeros at the end, this will be a lot easier to cut off if I do it that way. So if I write, hey, 5,000 R equals 4,000, how do I solve for R? Well, you divide both sides by 5,000 to figure it out. So I do 4,000 divided by 5,000 to figure it out. And if you were going in fraction form, guys, you divide both top and bottom by 1,000. Zeros cut off and you're left with 4/5. And that's what you do from one value to the next. I want to check if 3,200 times 4/5 equals 2,560. Hang on, I got to check this out for myself. I want to see if I got that right. 3,200 times 4/5. Yes, 2,560. I feel good in that nature. Anyway, there's the common ratio, and you can keep working from there. Excuse me. Anyway, that's what I want to see here. The division from one value to the one before it. What are you multiplying by? Do a division and show me what it is. I probably lost track of answering the question the way you wanted me to. Okay. Can you show us how to calculate the power of on a calculator again? So, I'm guessing they're asking where's the feature in the calculator to do it. And I don't know what to show specifically because every calculator is different. My phone calculator is different from my scientific or graphing calculator or anything like that. Let me show you some symbols that you can expect to find as a button. You can expect to find this button. I sometimes call it a caret. It's like that upward arrow. Maybe you'll see something that says like X to the Y or Y to the X. Something like that. I know on EdgeElastic we have like a blank box here and a blank box here that kind of shows, hey, we have something we're gonna type in here and we're gonna raise it like that. So there are just different buttons like that. So generally what you do is you type one of them. If I do 3 and then that button and 2, that's gonna give me the equivalent of 3 squared, which is gonna give me 9. So, yeah, that's the kind of thing I do there. I don't really know what else to say because I don't know all the different buttons there are based on calculators. Every one of them is different, and these are just some series of them. So you got to find what your calculator does. Like I said, my graphing calculator does something different from my phone calculator, which is something from Google's calculator, I'm sure. But eventually you'll find something that's the same. But to make it an exponent, there's something that has to be exponential-like. And on a keyboard, that arrow thing is Shift 6. That's Shift and 6. And that'll get you that little arrow thing as well, especially when we use edge elastic. Okay. Whoops. How or what can we do to make it easier for you to grade our homework or test? What? Are you saying I don't grade your tests on time? I grade your tests on time. It takes me a while. Oh, is that why you're asking? Are you saying, is it because I complain to my students a lot? It's my own doing. I write a lot of comments on tests and stuff. I do everything I can to help the students with their tests. So, what can you do to make it easier for me to grade stuff? And homework, I sometimes, my homework I can fall behind on. I'm used to having a TA, and the way that homework submission's done online is kind of weird. Here's what you can do. If you really want to do something, hang on. I have the hiccups. Let me pause this for 1 second here, guys. Okay. Back. All right, sorry. I was holding my breath for a while with the water. How or what can we do? Okay, so, all right, here's what you could do. Here's what you could do that's in your control. Generally, I spend a lot more time on homework when I have to write comments about something, either because you didn't copy down the assignment, you didn't complete the assignment, or something like that. So you could complete assignments, or you could not do them, but I'd prefer that you did them, of course. Because then I have to do other comments and stuff, skip things and say you didn't submit it. So if you complete the homework, then you're good. But here's what you can really do, and I don't know if I'm answering, the person I'm answering does this, or I'm not speaking to the majority of students either, but here's what students can really do. Stop cheating. You can stop cheating. The amount of time that I have to spend investigating, snooping around, and listen, I don't want to do it, but I want for it to stop. And that's the only way for me to do it, is to keep investigating. The more and more I have to investigate for students to be using Slater or Photomath or copying off each other or whatever umbrella, under the umbrella kind of thing that you do to cheat, is making me spend more time investigating it, and it takes a lot of time. So stop cheating. That's going to save a lot of time. Get more answers right on tests. That's not necessarily in your control. If you get something wrong, it's, I leave comments. But here's the thing also, if you don't want comments on your test, or if you feel like you're not doing exam corrections and things where the comments could help you, on this next test that we take, I'm going to give you a checkbox and say, check this box if you would like comments on the test or not. Or if you'd like them on the test. And then if you don't check the box, then it saves me a little bit of time. Just a little bit of time there. But no, even on your homework and your scratch work and stuff, make it neat and organized. Show your work. Copy down problems. Do everything in your power to make me have to leave less comments or to make you have less wrong. There's nothing you have to do, guys. I'm paid to grade. I'll bicker about it because it's just part of the job. It's just like anyone bickers for anything else as well. You don't have to do anything for me. I was saying, here's what you can do. And here's what you shouldn't be cheating. But, anything else is whatever. All right, thank you for the question. All right, how do you find the common ratio in geometric sequences? So I actually kind of answered that above right here. Can you show how to do the R equals whatever? I talk about kind of what this blank has to do with right here. And it really, I'll say it right now, you have to do a division of one number by the one before it. You have to do a division of one number by the one before it. So you'll see how I do that here. So I'll give you the timestamp to this specific question up there, and I hope that'll help answer it for you. All right, what is the difference between geometric... Wait, did we already answer... We answered that twice, right? Can you explain the difference? Yeah, so I already answered the difference between arithmetic and... Where is it? I already answered the difference between geometric and arithmetic sequence on a different question above. I'll give you the timestamp for that as well. Of course, I do expect for you to know this kind of stuff at this point. Geometric is common ratio, arithmetic is common difference, but there's more that I state there if you want to hear it. All right, how do you find the common ratio when the first term is a fraction? Well, so I kind of was mentioning here, and I'm not going to get too deep into it, but I kind of mentioned on a previous question how you generally want to try and find two clean integers, the smallest integers you can, often, but I showed one where it wasn't the smallest. You want to find two integers where you can divide most easily. And honestly, when a fraction's involved, it's probably less likely that you'd want to divide using one. Either divide from a fraction or divide by a fraction. It can get a little hectic. Now you just do division, which is multiplied by a reciprocal of the dividend. Divisor? I can't remember which one's which anymore. I'm a math teacher. I don't even know which one's divisor, which one's dividend. But find ones that aren't fractions. If the first term's a fraction, go to the next two terms. The point of a common ratio is it's the same ratio no matter which two terms you're looking at. From the first to second term, you're multiplying by some number. From the second to third term, you're multiplying by the same number. So I would just choose the second and third terms then and say, this times r equals this and divide. So I would just choose two other ones if possible. Otherwise, you divide with the multiply by reciprocal stuff. We'll see if people ask questions about that. Okay, next question. Why is something to the 0 power 1? Now, this goes not on sequences anymore, but this goes into the stuff where we're now graphing and plugging in x values that are not just 1, 2, 3, or 4, or whatever. So I don't know if I'm going to be able to. I can explain it, but it's with a property that you haven't done before. So I'm only going to be able to explain it in one way for you guys. Now, I haven't defined exponents for you in full the way that I would love to before, so I'll just write it right here. To me, the definition, I don't know if this is a mathematical definition or whatever, but to me, the definition of exponentiation is the number of times you multiply a value to itself starting from 1. Now, I know that when I put that in the definition, that helps explain why 1 is there because it's in the definition. But why is this a part of the definition? Why is it that if I wanted to do something like 2 to the 7th power, then I say starting from 1, I'm going to multiply 7 2's together? Well, because that allows you to, it starts to give the explanation as to why negative exponents, what they are at the same time. I'll get into that. But also, it kind of shows, it allows you to say we're multiplying 7 2's and we're also multiplying by 2 7 times. So not only is this multiplication symbol done 7 times, but the 2 also appears 7 times as well. Whereas if the 1 isn't there, there may be 7 2's, but there are only 6 multiplication items. So that's one way that it actually helps. It shows that, do I multiply 7 2's or by 2 7 times? Are the 7 multiplication symbols or 7 2's? To me, with this, the answer is yes. The answer is both. You do both. Let's look at it like a table, though. Let's do a bit of recursion and go from one value to the next like we would in a sequence. So in this format here, just kind of go fast. Let's say that we're looking at y equals 2 to the x power, and when x is 1, 2 to the first is 2. When x is 2, 2 squared is 4. When x is 3, 2 cubed is 8. When x is 4, 2 to the 4th is 16, and you can tell we're doubling each time. So I double 16 to get 32. I double 32 to get 64, and I double 64 to get 128. That is 2 to the 7th power. Now, as you notice here, we are multiplying by 2 as we go to the right. Every time x increases by 1, we go to the right. So there should be a pattern. If there's a pattern going to the right, then clearly there should be a pattern going to the left. If I multiply by 2 going to the right, that means going to the left, I am dividing by 2. Or you could say multiplying by 1/2. 16 divided by 2 is 8. Sorry, it's kind of hard to see my divided by 2's there. 8 divided by 2 is 4. 4 divided by 2 is 2. And when x is 0, what do you think happens? I got to take 2 and divide it by 2. This is like that 0th term, the thing that we're not really doing theoretically. 2 divided by 2 is 1. And this is going to happen for any such situation because any base raised to the first power will just be the base value out. So when I divide by that base value in and of itself, I'm going to get 1 back. And that's the best way that I can explain it for you guys right now. There's more of a proof version I could do if you knew how to divide bases with different exponents, or same base with different exponents, but I'm not going to get into that right now because it's not something we can do. But it still does just show that the number of times you multiply by 2 is equivalent to the x value that you're talking about if you start from 1. And this also helps explain negative exponents as well. I'm only going to do one of these here. So if this was to the negative first power, let's divide 1 by 2. Let's divide 1 by 2, and then we get 1/2. So you can see that if exponentiation represents the number of times you multiply by something, specifically positive exponents, negative exponents represents the number of times you divide something. So I divided by 2 once in this case. And if I divide by 2 again, it's the same as multiplying by 1/2. You'd get 1/4, and then you get 1/8 and stuff. It keeps going that way. Negative exponents doesn't mean negative numbers. I know you were asking more about 0, but that's why to the 0 power, it's 1. Whereas in multiplication, y is 2 times 0 equal to 0. How come? Y is 2 times 0 equals 0. Because to me, multiplication in that same format, guys, it's all about addition of numbers. Multiplication is the number of times you add a number to itself, starting from 0. Right? Because in multiplication, what kind of happens is I don't know. I guess I'm over-explaining now, but you just add the numbers over and over. From 0, I add 2 once and twice and 3 times. 2 times 7. 2 plus 2 plus 2, 7 times. But starting from 0, I add 2 over and over. If I don't add 2 at all, it starts from 0. I don't know. But that's a good part of the definition that I like to use for multiplication and for exponentiation that allows you to say, okay, that's where we begin from, and then that's where everything carries from afterward, whether I go positive or negative. Okay, I hope I answered the question because I went pretty deep into that one. Let's move on. When solving a geometric and arithmetic sequences, out of the two formulas that you have taught us, does it matter which formula we use? Well, I've only taught you the explicit formula for each. We have saved away from the recursive formula, and we have not used the explicit formula for the 0th term, f of 0. I kind of wrote one of them down earlier in this video, but we haven't been using them. So does it matter which one you use? There's only the explicit rule features a common difference, so it's important that you use the one that features a common difference. So the explicit, for an arithmetic sequence. So an arithmetic sequence explicit rule is going to look like this. Oh, you know what? You might be asking about subscript versus function notation. If you're talking about this versus this, it doesn't matter. I mean, if the problem presents itself in one notation, I would ask you to continue it. And geometric is here. But you can't use an arithmetic rule for geometric sequence or anything like that because this doesn't have a common ratio. The whole idea about the common difference is you're adding it a certain number of times. Common ratio, you're multiplying a certain number of times. But whether you're talking about that function versus subscript notation, that's irrelevant. If I use geometric, I can use one or the other interchangeably. It'll be the same thing. But if they give me a table and it says f of n, or if they say if they say find f of 12, I should be using function notation for that. It's only proper that you use what they ask in those cases. But no, they're just different notations. I kind of answered that before. Different notations doesn't mean anything different. Okay, when dividing fractions, why can't you just multiply the top by the bottom and the bottom by the top? Wait, where is it? Sorry, I lost the thing because I'm about to write this. When dividing fractions, why can't you multiply? So let's say we have 2/3. I'll just do two different sets of fractions so it's not too confusing. 2/3, like it's fractions, it's confusing. 2/3 divided by, 4/9. Okay. When we divide any numbers, but fractions especially because you can see both top and bottom, when you divide fractions, it's the same as multiplying by the second guy's reciprocal, so times 9/4. And when you multiply fractions, you multiply straight across. 2 times 9, 3 times 4. Let me just clean this one up and that'll answer the question. 18/12, I can reduce that to 3/2. Beautiful. Now what they're asking, it sounds like what they're asking is why can't I leave it right here instead of writing it like this and just do 2 times 9 and 3 times 4? I'll give you 2 reasons why you shouldn't. Number 1, I'm not seeing multiplication. Well, actually 3 reasons. Number 1, I'm not seeing multiplication right here. This looks like division. Number 2, who's to say you're going to put these in the right spot? 2 times 9, it looks like I'm about to put 2 times 9 right down here and make that 18. It looks like 3 times 4, it looks like I'm going to put that up there and put 12. I mean, what spot do they go into? How would you know what spot to... Oh gosh, I got to pause this thing again. The hiccups. All right, we'll try my best, see if they're gone. Okay, now the sniffles are back. All right, so 2 times 9, I mean, who knows where you're going to put these things eventually? Some people are just going to put them all in the wrong spots. This isn't an ideal form of multiplication. It's not a rule that we see. But division is multiplication by the reciprocal. That's a mathematical property. Multiplying straight across, that's a mathematical property. I know 2 times 9 will go on top, 3 times 4 will go on bottom. The third reason we shouldn't do it, because this is clearly wrong. The third reason is because you might confuse it, because you wouldn't be the only person who ends up doing this. I don't know if you guys know anything about proportions here. Let me get rid of this. I don't know if you guys know anything about proportions, where if I said something like, oh, solve for x over 2 equals 2 over 5, something like that. And there's this thing called cross multiplication, which means the 5 multiplies with the x and the 2 multiplies with the 2. 5x equals 4, divided by 5x equals 4/5. That's great. You have a way of cross multiplying. It basically busts the fraction. It's not in the way. And it's this great magic step where things just go up there and they multiply. Now, there's a reason behind cross multiplication that makes this work. In a proportion with an equation, we are actually multiplying both sides by 5, which means the 5's go away here. That's why there's no more 5 on this side of the equation in the denominator. And you also multiply both sides by 2, which makes the 2's go away right here. And you can see that 2 multiplies with 2, you get 4. 5 multiplies with x, you get 5x. Cross multiplication is just the visual version of having someone, it's the training wheels version of having someone say, okay, this makes this a lot easier now that I know this. But it's not a magic step. You can't do it just because. We do it specifically for proportion. I don't know how many times people actually, when we're multiplying a fraction, like the one we talked about before, where it's I forgot what numbers I used, 2/3, and I was dividing 4/9. I think I was, I think it was this. So if I write, 2/3 times 9/4, I mean, it doesn't matter which way you write it. The point is, this idea of cross multiplication, it's a magic step in and of itself already. You don't want to misconfuse it for something where you're not supposed to be using it. That's in either case here. Some people might think, cross multiply, or cross multiply, or whatever it is. I mean, this is definitely wrong. This at least holds some merit because 2 should be multiplying with 9 as we multiply straight across. But cross multiplication, get that out of the way. Some books don't even use the phrase anymore. They want to make sure that they don't pull into poor habits with students. When you learn and understand what it is and when you use it, go ahead, because that's what I do. I don't draw the arrows, but I know what I'm doing with it. But here, they misuse it in cases where they don't exist. So you want to get as little into the cross multiplication stuff as you can in times when it's not supposed to be used, and this is one of those cases here. So I'd stave away from the concept of multiplying across in that way, drawing arrows that way. Just use the multiplication rule that we're supposed to be using when it comes to multiplying, which is multiplying straight across, like this right here. And those are the 3 reasons I would just do that. But dividing is multiplying by the reciprocal of the second guy. You don't flip the first guy, you just flip the second guy. Okay, there it is for that question. Thank you for asking that. It's a really good question. Okay, is it better to graph a mixed number or as an improper fraction? Well, if you're talking about actually graphing it, it's better to graph a mixed number, because if I have the number 9 halves, I need to know where that goes on a graph. Unless you want to count halves, unless from 1/2 you want to count 1/2, 2 halves, 3 halves, that's fine. But if you turn it into 4.5, then you know it's a number between 4 and 5. If you're talking about calculating points and getting points in your table so you can plot your graph, I like the improper fraction, especially when I'm going from one number to the next. It kind of saves me opportunity and time. And if I have to use a calculator to get what numbers it's between, I can do that as well. But the mixed number isn't really used much anymore. I mean, we get an answer, we write it, it's perfect, it's exact. Improper doesn't necessarily mean bad. It's just that you have more in your numerator, your partial than your whole. I understand why they call it. But get used to improper fractions. You're going to see them a lot more. But if you're graphing, I mean, you want the mixed number so you know where it's between. Where is 9 halves? It's between 4 and 5, kind of that way. All right, what's the difference between explicit and recursive? I'll say this in 2 ways. I'll answer it in a second, but I do want to say that I did answer this last semester. So if you want me to find a link to a video thing where I get in deeper detail, I can. I'll also say this. We're not dabbling into recursive equations so much, even though we're using recursive logic. So here's what the differences are. And I'm not going to write out the explicit formula or the recursive formula. Hopefully you can get it just by hearing it. Working recursively in a problem is looping and reiterating, going from one value to the next. If my first term is 5 and my common ratio is 2, to find the second term, I'm going to take the first term and double it, because I start with 5 and multiply by 2. I get 10. To find the third term, I take 10, multiply that by 2, and I get 20. 20 times 2 is 40. 40 times 2 is 80. 80 times 2 is 160. To get the next term, I'm taking the value of the term before it to do something. That's recursion, because I'm just constantly going to the next term from the term before it. So to find the 20th term with recursion, I got to multiply 5 by 2 to get the second term, by 2 to get the third term, by 2 to get the fourth term. And I got to do it 19 times over and over to get the 19th term, and then take the value of whatever that 19th term is to then multiply by 2 and get the 20th term. So recursion is good to go from one number to the next pretty closely, but if I want to find the 20th term or the 100th term, I might want to do something else, which is just, in a nutshell, use the explicit rule. Now, the explicit rule, as it's written, has an exponent to it, and an exponent describes how many times you multiply by a number. So if I start from the first term and I say I got to multiply by 2 19 times, because that's the 20 minus 1, I'll do 2 to the 19th power and say, what is 2 times 2 19 times first? Let's figure out what that is. It's huge. I don't know what it is. It's a big number in the millions, near a million. And then I do that times 5 and it figures it out. So the explicit rule finds any term imaginable that you want at the drop of a hat. You got to calculate it, but it comes at the drop of a hat through a substitution of your number. To find the 20th term, I actually plug 20 into my formula. I just 20 minus 1 to get 19, but I actually plug 20 in my formula. The recursive rule states to find something like the 20th term, I got to multiply by 2 to get the next term, and the next term, and the next term, until I get to the 20th term from the 19th term, something like that. So anyway, there are other things. I can find you another link there. We haven't been using recursive formula, although we've been using recursive logic to go from one value. Like to find the next 3 terms in a list, we do times 2, times 2, times 2. And I think that's easier than plugging 5 into the rule, and plugging 6 into the rule, and plugging 7 into the rule. Okay, in an explicit rule, if our exponent is negative, what do we do? These hiccups can't go away, guys. Well, as far as we haven't had to do it yet until we've started to hit, because if you say explicit rule, I'm hearing geometric sequence in my head, and you wouldn't have a negative exponent because geometric sequences start with a domain of 1. And at worst, you'll raise it to the 0 power, but never negative. So let's ignore the term explicit rule. Let's just say in an exponential function, if our exponent is negative, what do we do? I guess you could use a calculator, but if I'm refraining from having you use a calculator, the rule behind exponential, negative exponents is, and let's see, they've been using the letters, they used C and N in our book. So if I have some base raised to a negative exponent, its positive exponent equivalent is bringing it in the denominator like this. So if I have a rule that says something like 3 times 2 to the x power, like that, and I want to substitute, let's use f of x so you know what I'm directly substituting here. Let's say f of x, and I want to find out what f of negative 2 is. That's going to be 3 times 2 to the negative second power. Now 2 to the negative second power, if I go by this right here, that would be 1 over 2 squared. So this becomes 3 times 1 over 2 squared. 2 squared is 4. Sorry about that. 2 squared is 4. So I get 3 times 1/4, and that becomes 3/4. So you use that property in that way. So this is how the property is written out. Because negative exponents, as I said in another question, describes how many times you divide by your number. If we divide by 2 twice, that is equivalent to dividing by 4, essentially. If your exponent is negative inside a fraction, it actually becomes positive in the numerator like that. And we actually saw a third version of this where if you have a full-on fraction, as in the top and bottom are non-1 values, just like this last one, just like these last 2 guys, you're basically flipping the fraction. So if you see it in a quantity, I forget what variables I used, let's say a and b. A and b to the x power here, that becomes, to the negative x power, that becomes, you flip the inside, that becomes b over a to the x power here. So same thing, reciprocal, 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 no matter which ones you do there. You flip it to make the exponent positive. And there's more that you can do from that property here on out afterward. Doesn't matter what the letters are. The point is what you're doing. So I hope that makes sense. Negative exponents has nothing to do with negative numbers. That's for sure. Okay, here we go. What happens if your common ratio is negative? How does it affect your answer? Well, a common ratio is for a geometric sequence, which means you're multiplying. Whereas in an arithmetic sequence, you're adding a negative. Adding a negative is just subtracting. But in a geometric sequence, every time you multiply by a negative, your sign is alternating. So let's say we had a list that went like this. Or let me give you the rules. The value of the first term is 1, and the common ratio is negative 2. Well, our first term is 1, and when we multiply that by negative 2, we get negative 2. Multiply that by negative 2, you get positive 4. Multiply that by negative 2, you get negative 8 and 16. What happens is your signs alternate. Your numbers get bigger in their respective direction, positive or negative, but the signs alternate. If I looked at this as a graph, and given that it's a sequence, this will be a discrete graph, but if I graph these points as a graph here, if I plotted these points as a graph, I'd get 1, 1, and then 2, negative 2, and then 3, 4, and then 4, negative 8. And you can see this kind of pattern where it goes up and down and up and down. And you might imagine it goes like this. And you might imagine that because I said this was a discrete function, you might say, well, if it's a continuous function, then do you connect the dots like this? This is the concept that's kind of occurring, but you wouldn't connect the dots. I know this isn't a part of your question. You wouldn't connect even though this is the concept that kind of feels like it's occurring because it's going up and down and up and down. I understand that. But this isn't what would actually happen, because when we raise a negative base to a fractional exponent of any sort, remember this is 1 and this is 2 and this is 3, but anything in between, a negative base to a fractional exponent often bodes not well, and it leads to imaginary values. So we actually can't connect the dots because there isn't anything in between to plot. That's why when we're doing y equals ab to the x, when we do y equals ab to the x power, guys, we're only going to be looking at b values that are greater than 0, and also b values that are not 1 for a different reason, but only positive b values because these are continuous functions. And in continuous functions, we need to be able to connect the dots, and they wouldn't connect if b was negative. So what happens in R? The signs alternate because multiplying by a negative changes the sign. And on graph, it kind of goes that up, down, up, down. It goes larger negative, or if the common ratio is a fraction, it goes smaller negative, but it goes above and below, and it kind of separates, which is kind of cool. Okay, moving on forward. When dividing fractions, why can't you just multiply the... Okay. By the way, I saw this tab was open with the answer blank. I don't know if I already asked. Okay, so I already answered that. I hope you got your answer before. All right, 3 more questions. When there is not a proper way to identify a sequence... When is there not a proper way to identify a sequence if the sequence doesn't have a pattern? If we're talking about a sequence, it's likely there is a pattern. It might be hard for you to find, but it's likely there is some pattern in some way. You guys have probably seen the Fibonacci sequence before, where recursively, I get to use the word, recursively you add the previous 2 values to get the next value. 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13. There's a natural occurrence to this thing that I absolutely love. If you Google it, you'll find what it is that I'm referring to here in the Fibonacci sequence right there. And that might be harder to find because you're like, well, this is plus 0 and plus 1 and plus 1 and plus 2. Unless you notice that that other number was the one before it that you're taking with that, you might not notice that's a Fibonacci sequence. Anyway, most sequences in math should have a pattern. Otherwise, it's a random list of numbers, and it just doesn't have that. It's just a list. It's not a sequence. A sequence is a list of numbers to follow a mathematical pattern. What if you can't find it? Well, then it's neither arithmetic nor geometric, and to me, that's all you need to know at this point. That being said, and I wish I got resources to help me. I wish I prepped this question and showed you. But there are some textbooks, algebra textbooks and whatever, that use these tiles, and you use the tiles to help describe what kind of growth pattern is occurring, and that helps you find out what's happening from one number to the next. It's hard to explain in this scenario here, but like maybe you don't see a pattern here from 2 to 5 to 10 to 17 to 26 to 37 to like this. But what I happen to know is that this isn't as good to find in recursion. Well, I guess in recursion you could kind of say, see how this is plus 3 and plus 5 and plus 7 and plus 9. You could probably use that to kind of refer to something there, and that's the concept of this pattern here, because this is a quadratic equation. What's happening is if this is your first term, second term, third term, etc., what's happening is this is actually this is neither arithmetic nor geometric. What's happening is you're squaring your term number and you're adding 1 to it. 1 squared is 1 plus 1 is 2. 2 squared is 4 plus 1 is 5. 3 squared is 9 plus 1 is 10. And that continues. So some are harder to find, but those the patterns with tiles really do help you find it a little bit better because you look at the growth in a different way. But that involves you knowing quadratics a little more. And all I'll say is that all you're trying to seek is there a common difference, in which case it's arithmetic. Is there a common ratio? If so, in which case it's geometric. Otherwise, it's neither. And this neither has a common difference nor a common ratio, so you're good. But yeah, all of them should have a mathematical pattern, even if it's hard to find. Okay. Last 2. How do you turn fractions into decimals and decimals into fractions? Well, most calculators have a button. You can just press it and it'll do it. Now, I'm assuming that when you say decimals into fractions, that it actually can become a fraction, because there can be an irrational number that's a decimal, like the square root of 2, and now there's no integer fraction version of it. How do you turn fractions into decimals? You divide. You do long division. Let's do a number that can't divide very well. Let's do let's start easy. Let's do 1 divided by 2. 1 divided by 2. So long division. I'm not going to teach you how to do long division, but kind of do it at the same time. 2 can't go into 1 any number of times, so you got to add the decimal here, and you add a 0. 2 goes into 10 5 times, so there's that 0.5. 2 times 5 is 10. 10 minus 10 is 0. So you're left with 0.5, and that ends being the number. Pretty easy long division. But you do something like 4 divided by 11. 4 divided by 11. 11 can't go into 4 a certain number of times, so you add the 0, then you get 40. 11 can go into 43 times. 11 times 3 is 33. Subtract those two numbers, you get 7. 11 can't go into 7, so you go to the different number. You add a 0 right there. 11 goes into 76 times. 11 times 6 is 66, and you get a 4 back. And this thing's going to repeat itself at this case here. 1143 times, etc. It keeps going. And you're going to keep getting 3, 6, 3, 6, 3, 6, and there's the decimal equivalent of that, a repeating one, 0.36 repeating. So it's long division. Any division, unless it terminates, unless it ends, it will repeat itself as long as it's a fraction of two integers. How long until it repeats itself? Every number changes. 1/9 is 0.111111. 1/3 is 0.33333. This has two decimals. 1/7 has like 6 or 7 decimals, things like that. So you use long division to figure that out. How do you convert fractions into decimals? How do you convert decimals into fractions is a different story. Sometimes, listen, if the number ends, if we're talking about 0.5, we mentioned that before, find out where it ends and find out how many decimals you had to move over to get your value. So you might know that multiplying here, before I do that, 5 times 10, it's not just, it is 50, but the reason is because every time you multiply by a power of 10, you take the decimal in 5 and you shift it 1 to the right. So the decimal goes from here to here, and what takes its place is a 0. So every power of 10 you multiply by, you shift the decimal 1 place to the right. Every time you divide by a power of 10, you shift 1 decimal place to the left. So, I'm sorry guys for the hiccups. Let me pause this again. Okay, I'm all out of water, so I hope this lasts me. I hope I don't hiccup again. I could always refill more water, but I want to finish this strong. Okay, so I was just mentioning that, 0.5, it's a version of 5, it was shifted. From 5, I shifted 1 decimal place to the left. The way that happens is if you take your number 5 and if you divide by 10. 5 divided by 10 gives you 0.5. That's because that's the knowledge of dividing by certain powers of 10 makes your decimal shift places over. If I did 5 divided by 100, that is 0.05 because it's 2 decimal shifts over because the 100. And 5 divided by 1,000 is 0.005. Oops, 0.5. So you keep shifting the decimal over to the left as you divide by powers of 10. So if your decimal terminates, you can always write something in that form. So 0.5 is 5/10. Of course, after that, you'd want to reduce your fraction. So divide top and bottom by 5, and then you get your 1/2. Now, another way is in some of these numbers, like most people know 0.5 is 1/2. So if you just know it, that also works. What if I get something like 0.125? Because I know what this fraction is here, 0.125. Well, this was shifted. This is 125 shifted over 3 decimal places here. So what I'm going to do is I'm going to rewrite this as 125 over a 1 followed by 3 zeros, 1,000. 125 over 1,000 is 0.125. And if I reduce this fraction here, you can divide. If you don't know what to divide by, quarters work here. Divide by 25 to start, 25 over 25. And that would leave you with 5 over 40. And then I can divide top and bottom by 5. That leaves you with 1/8. So this is 1/8. That's its equivalent. You got to reduce the fraction afterward. And that's how you do something when a decimal terminates there, is you got to divide it by a certain power of 10 and then reduce the fraction from there if you can. Most of the time you can. Not always. How do you do it with repeating decimal? Let's go to that 0.36 example. 0.36 repeating is the decimal. How do we figure out this is 4/11ths? This one's a little trickier. I'm only going to kind of show it once and then explain what you can do after that. Because repeating decimals does have to do with dividing by a certain number. I'm actually going to write a couple 3/6s. Just please make sure you know that this does repeat forever. 0.36, 36, 36, 36. What I'm going to do is I'm going to find out where the repeat happens. So I see that this 3/6 repeats itself. So I'm going to present this in a way. I'm going to set x equal to this whole number here. And then what I'm going to do is I'm going to multiply by the number that brings this into the integers column, into the whole numbers column, and leave the rest as decimals here. So I'm going to move the decimal 2 places over by multiplying by 100. If I multiply the left side by 100, I get 100x. If I multiply the right side by 100, I get 36.3636 repeating, etc. 3636 dot 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 dot. Why does this help me? Because now I can subtract x from both sides. Check this out. I subtract x from this side, and you know what x is? X is this number here. You know what happens when I subtract 36.363636 with 0.36363636? These cancel. That whole thing's gone. You're left with just 36 on the right side, and on the left side you're left with 100x minus x, which is 99x. You divide both sides by 99, and that is your fraction. It might not be reduced, so let's reduce it. I can divide top and bottom by 9. 36 divided by 9 is 4. 99 divided by 9 is 11. I get 4/11ths. When you have a repeating decimal, find out where the repeat is and divide it. This was the long way, but you divide it by a series of 9s afterward. You divide it by a series of 9s afterward, and then you reduce the fraction. How many 9s? Pretty much as many 9s as the digits you're referring to, unless there was a 0 to lead the way or something like that. It's kind of hard to explain. It gets a little tough. It's weird to do. If I had something like, let's see, let me figure out what 1/7 is. I know it's 0.14 something. So 1/7 is 0.142857. 142857. It keeps repeating, right? So you see the 142857 repeating itself there and then there. What you can do besides all the algebra stuff I showed, take 142857 and divide it by 9999999. This is the bigger number, just barely, and the repeat is a result of having a bunch of 9s divided. Now, I'm not going to reduce that fraction for you, but I guess you can divide top and bottom by 142857, and you would actually get 1/7. Let me check that. 9999999 divided by 1428. Oops, that's a 5. 8. Oops. Shoot. 8. Oh, crap. I messed up. And I know you can't see what I'm doing on the screen right now. 142857. Yep, that's 7. So yeah, that's what those things do, divided by a certain number of 9s. If there was a 0 in front like that, then you got to get an extra 9 in there. And another 0 in front, another extra 9. So that's how you do that. I'm not asking you to do that. I'm sure no other teacher's really going to ask you to do that, but that's how you do it. Thank you for asking. All right, and the last question here is, I got confused on how you find f equals f of n minus 1 or like that. How do you find those and put them in the right spot? Well, this almost looks like a recursive rule when you're saying f of n minus 1. So if you're just not sure what the formula looks like, it literally is a substitution. That's as best as I can say. When you have access to your own formula, when you have this, I'm going to write the explicit formula of a geometric sequence. And we're asking you to write the rule. The rule says for any value n. That means we leave n as the variable. This stays here. This stays here until I ask you for an n. Find the 12th term, plug in 12, all that. All we got to do is substitute something for f of 1, and something for r. F of 1 represents the value of the first term, so you find the value of the first term, and then you plug it into here. For all of f of 1. R represents the common ratio, so you find the common ratio of whatever it is. To make it easy, let's do a problem. Let's do 3. Let's do different numbers. 5, 15, 45, 135, etc. Okay, well, we find out that the first term is 5 because it's right there. And the common ratio, you can do 15 divided by 5, which is 3. So that's r. So all you do is you substitute. Instead of f of 1, you're going to write 5. Not f of 5, you're just going to write 5. It's going to take f of 1's place. I kind of ran out of room, so let me kind of put it right here. So instead, we're going to write f of n equals 5. 5 just took f of 1's place. Times r. R is 3. R is 3. 3 is going to take r's place. It's the n minus 1 power. It's a straight substitution. That's all I can say. It's a straight substitution once you figure out what those two values are. And then I might ask you to find the value of the 12th term. So from this rule, you substitute 12 in for n, and 12 minus 1 is 11, so 5 times 3 to the 11th power, and then you compute it. But the rule helps start it off, and then you kind of carry on from there. Okay. All right, so I hope that answered all your questions, guys. I hope that took care of this. If you want to see timestamps of anything, they are down below. And that's it. Take care. I'll see you in 2 weeks. Thank you.